So, welcome you all to IIT-PAL program. Myself Punyamurthy from Department of Chemistry, IIT Guwahati. Today, we will study about the part 2 about alkenes. In the last class, we have seen the part 1 of alkenes and structure, nomenclature, isomerism, preparation and physical properties of alkenes. Today, we will study about the chemical properties of alkenes. Alkenes are rich source of having bi electrons. Therefore, they undergo addition reactions with the electrophiles to give the corresponding addition products. So, today we are going to look at some of the common reactions. The addition of hydrogen, addition of halogen, addition of hydrogen halide, addition of sulfuric acid, addition of water, oxidation reaction. So, there will be two types of reactions we will study: oxidation of alkenes to diols and carboxylic acids, then dicarbonyl compounds like aldehydes, ketones, that is ozonolysis. At the end, we will study about the polymerization. These are very important reactions, and let us now focus on the addition of hydrogen. As we have seen the beginning of the hydrogenation of alkenes to alkanes, and so alkenes can be converted into alkanes using one equivalent of hydrogen. For example, if we have here ethylene, and when you treat ethylene with hydrogen, one molecule of hydrogen, in the presence of catalysts like palladium, platinum and nickel, the hydrogen can undergo addition to the alkene you get alkane. If you look at the reaction, as I mentioned earlier, the reaction is stereospecific. The both hydrogen atoms come the same side of the alkene. It can be the bottom side or top side. This in addition takes place, and in this reaction, as I mentioned earlier, what happens? You have the metal surface. The metal surface, the hydrogen is adsorbed first. Then your alkene also adsorbed on the metal surface by you have the carbon-carbon double bond. There will be interaction between the bi bond and your metal. Now, once for example, when you pass hydrogen, the hydrogen will be adsorbed in the surface of the metal, and when you add alkene, the alkene now it can also absorb, it can interact with your metal. you have the alkene here. Now, the hydrogen whatever absorbed from the metal surface can be transferred to the alkene, you will get the metal alkyl intermediate. You have this kind of intermediate. Now, another hydrogen, when since the reaction is carried out in the presence of hydrogen pressure, another hydrogen can bind here. This hydrogen can transfer again, you will get your alkane. The both hydrogens are added the same side of the alkene, the reaction is syn addition reaction stereospecific. So, when you have different substituents, the reaction of course, you will get the selective addition product. So, the next example is addition to halogen. It is a electrophilic addition reactions, and like when you have the alkene, for example, ethylene, when you react ethylene with, for example, Br2 or chlorine, under this iodine does not undergo addition with alkene normal conditions. However, bromine readily undergo reactions in the presence of in CCl4. When you carry out the reaction, the bromine undergoes addition to give the vicinal dibromo compound. And similarly, chlorine also can be added. You get 1,2-digaloalkanes. So, in these reactions, if you regarding the mechanism, let us see the bromination reaction. Alkene the double bond attacks the bromine, you get brominium intermediate. So, this brominium ion intermediate undergoes reaction with this Br minus. It acts as a nucleophile, it attacks this, it can attack this carbon or that carbon. Suppose if it reacts here, this anti to this bromine, you will get this 1,2-thiolaloalkanes. So, if you look at this compound, this also stereospecific reaction, this addition of the bromine takes place anti addition. If you look at it, and this is just opposite to this bromine, you get this anti addition product. Suppose if you react with this alkene trans to butene with the bromine, you will get this dibromo 2,3-dibromobutane. On the other hand, if you have this cis-2-butene, it can lead to mixture of enantiomers. You will study the stereochemistry of these reactions in our in higher class. Depends upon the substrate. When you have this kind of substrate, then you can get stereoisomers. You can get enantiomer in this case. Of course, in this case, you will get a compound which has planar symmetry, and it is a meso compound. We will study in details in the higher class. The next reaction is addition of hydrogen halides to alkenes. This also electrophilic addition reaction, just we have seen the addition of bromine to alkene is an example for electrophilic addition reaction. And in this case, the reactivity of alkyl halides is hydrogen iodide is more reactive comparing to HBr. HBr is more reactive comparing to HCl. This is the reactivity order of hydrogen halides towards alkenes. Now, let us take HBr. If you react with symmetrical alkenes, so you will get 2-bromobutane. Other hand, if you take unsymmetrical alkenes, for example, propene, when you react with the propene with HBr, so you will end up with mixture of compounds. There is a possibility of formation of these two compounds, and however, in this case this will be the major compound, this will be a minor product. So, let us see the mechanism of the reaction, we can understand. So, I mentioned this is an example for electrophilic addition reaction. So, the alkene reacts with the HBr to generate the carbocation intermediate. So, this carbocation intermediate reacts with the bromine Br minus, the addition product. So, if alternatively it can also form a primary carbocation So, in this case, if the carbocation reacts with the Br minus, you get the primary alkyl halide. So, there is a possibility of formation of both these carbocations. However, the secondary carbocation is more stable comparing to the primary carbocation. So, the formation of this predominant in this case, therefore, and we get this as a major product. This because we will study in the higher class again, that when you have the more substituted carbocation, for example, tertiary carbocation or secondary carbocation, they are more stabilized by hyperconjugation as well as inductive effect, and this therefore, this more stable, the concentration of this formation of this carbocation is higher than this, therefore, we get this as a major compound. So, during 1863, the Russian scientist is called Markovnikov. He studied a reaction of a series of experiments with this substrate. He found that, he observed that, and so the electrophilic addition reactions like addition of hydrogen halide to alkenes, and always the Br minus, the negative ion species undergoes addition to the carbon which has less hydrogen atoms, and in this case if you look at it, this has the 1 hydrogen atoms, therefore, the Br minus undergoes addition here and you get this a major compound. This we call it as, it follows the Markovnikov rule product. So, it depends upon the reaction conditions, and alkenes can undergo addition with the hydrogen halides, for example, hydrogen bromide to give the more substituted alkyl bromide. On the other hand, if the reaction is carried out in the presence of like peroxides, you get the opposite addition product, otherwise regioisomer. And let us look at this reaction. When you react with propene with hydrogen bromide in the presence of peroxide, you get a mixture of compounds. This is a major product, this is minor product. Just we have seen the case of electrophilic addition reaction, always this is the major product. However, when you carry out the reaction in the presence of peroxide, this is going to be the major product, this is going to be minor product. This is called anti-Markovnikov product. And in this reaction, particularly when you carry out the reaction in the presence of peroxide, you get this as a major product. Now, let us look at the mechanism. In this case, what happens? The peroxide, let us take benzoyl peroxide. When you heat the reaction, the peroxide can undergo homolysis. The presence of light also, it can undergo homolysis to give radicals. So, this can lose carbon dioxide, you get phenyl radical, 2 molecule of phenyl radical. Once you form this radical can react with your HBr. Can lead to the formation of benzene and Br radical. This Br radical now can undergo addition to the alkene. On the other hand, you can also undergo addition with this carbon, then you will get the primary radical. If you look at these two radicals, as just we have seen, when you have the secondary carbocation is more stable compared to the primary carbocation, because it can be stabilized by hyperconjugation, same thing here also, and this secondary radical is more stable comparing to the primary one. So, the formation of this radical will be more comparing to that. Once you form this radical can now react with another HBr. So, this can abstract the hydrogen atom. So, you will get alkyl halide, primary alkyl halide, and similarly this can react with HBr, can abstract the hydrogen atom. So, you will get in this case secondary alkyl halide. So, whenever you carry out the reaction in the presence of peroxide, therefore, we get this primary alkyl halide as major compound, because the formation of the secondary radical in this case, and you get this major compound. This is called anti-Marconico product. This was discovered by Harash and Mayo. During 1933, they have discovered this addition of hydrogen halide to alkenes in the presence of peroxides. They found that when the reaction is carried out in the presence of peroxide, always the primary alkyl halide is formed as a major product. And however, if you look at these two addition of hydrogen halides to alkenes, the previous case, the electrophilic addition reactions and hydrogen iodide, hydrogen chloride, hydrogen bromide, all can be added to alkenes, but in this case under peroxide conditions only hydrogen bromide undergoes addition to alkene, and the hydrogen HCl does not react under these conditions, the bond is strong. And in the case of hydrogen iodide, and what happens when you generate the I radical, these two I radical combine together, you convert into I2. Therefore, this reaction, particularly the addition of hydrogen halide, hydrogen bromide works very well with alkene, the presence of peroxide, HCl and HI do not work under these conditions. So far, we have seen three types of three reactions. First, addition of hydrogen we have seen is a stereospecific addition reaction. Then we have seen the addition of halogen, it is a electrophilic addition reaction. Following that, we have seen the addition of hydrogen halide to alkenes. First, we have seen the electrophilic addition reactions. Later, we have seen the radical reactions where hydrogen bromide undergoes addition to alkenes to give the primary alkyl bromides. Now, let us look at the addition of sulfuric acid to alkenes to give alkyl sulfates. Let us take propene as an example. When you treat propene with cold sulfuric acid, concentrated sulfuric acid, cold conditions undergoes addition to give and secondary alkyl sulfate as the major product in this reaction. This reaction also involves electrophilic addition reaction, and in this case what happens, if you look at the mechanism, as we have seen earlier, the double bond attacks this one. You form a more stable secondary carbocation. This carbocation reacts with to give the corresponding alkyl sulfide. This is also an example for electrophilic addition reaction, and this carbocation is a planar molecule, right. This this can the sulfate this SO4 H minus can undergo addition to the top side or bottom side of the carbocation, but you will get the secondary alkyl sulfate. The next example is addition of water. Alkene can undergo addition to water in the presence of a few drops of sulfuric acid to give secondary alcohol. Let us take this unsymmetrical alkene. When you treat this alkene with water in the presence of few drops of sulfuric acid, it undergoes hydration to give secondary alcohol. This is the major product. This is also an example for electrophilic addition reaction. Regarding the mechanism, you form oxonium intermediate, and this undergoes reaction with our alkene. So, you generate the carbocation as we have seen earlier. This carbocation now undergoes addition with our water, it is a nucleophile. This can remove proton, you get secondary alcohol. The next example is oxidation reaction. So, we are going to look at two types of oxidation reactions. First, the oxidation of alkenes to diol using potassium permanganate. when you treat alkene with aqueous dilute, cold permanganate and room 0 degree, this alkene can undergo oxidation to the corresponding diol, vicinal diol. In this case, the hydrogen or the OH group comes to the same side of the alkene. This is in the addition reaction, and the reaction conditions is very important. You have to carry out the reaction, mild reaction conditions using aqueous, dilute, KMnO4 and cold reaction conditions. Then you can partially oxidize the alkenes to diol. On the other hand, if you oxidize the alkene using acidic KMnO4 or potassium dichromate under heating conditions, this alkene can be further oxidized into carboxylic acid depends on the substrate in this case, and it will be oxidized to acetic acid and carbon dioxide, and it depends upon the reaction conditions. If acidic, there will be over oxidized to carboxylic acid. If you carry out the reaction under mild reaction, cold, if you use 0 degree temperature and very dilute potassium permanganate, you can try to stop the oxidation reaction in the diol stage. On the other hand, if you use strong oxidizing agent like acidic KMnO4 and warmer conditions, and then it can undergo further oxidation into the corresponding carboxylic acid, and it depends upon the substrate. For example, if you use this one, you get acetic acid and carbon dioxide, and if you use this alkene, if you apply these reaction conditions, you get here ketone you get acetone plus acetic acid. It depends upon the substrate, and you will get ketone or carboxylic acid or carbon dioxide. So, you will study the mechanism of this reaction in our higher studies in detail, but what happens basically in these reactions? And this alkene, let us take for example, this ethylene, and what happens, it undergoes addition with your KMnO4. So, KMnO4 plus 7 state, and what happens, this alkene undergoes addition, this electron comes to the manganese, and this undergoes addition with this carbon, and basically it is a cycle addition 2 plus 3 cycle addition reaction. You will get a cyclic intermediate, first it forms this cyclic intermediate, and it depends upon the reaction conditions. If very if you use dilute aqueous KMnO4 and cold conditions, and this what happens, it undergoes hydrolysis, you get the diol. On the other hand, if you use acidic potassium permanganate or dichromate, it undergoes cleavage. You get aldehyde. You get aldehyde. That aldehyde further reacts with water. You have in aqueous medium, you have water. It can form and it further can be oxidized in carboxylic acid. This is what happens here, and it depends upon the substrates and the reaction conditions. You can try to selectively convert into cis diol or the corresponding carboxylic acids. The next example is ozonolysis. Alkanes can be readily converted into aldehydes ketones or carboxylic acid using ozone, and in this reaction ozone undergoes addition with this alkene and forms first. Let me write the product. In this case, you will get the dialdehydes. And acetaldehyde and formaldehyde, and if you look at the mechanism, the alkene undergoes addition with ozone. Let us take ethylene. It undergoes cycle addition to give one comma 3 cycle addition reaction. This is not stable intermediate, it undergoes cleavage. You can call this retiro 1,3 cycle addition reaction. You will have carbonyl oxide and a carbonyl group. Have this can further undergo cycle addition reaction. This is called ozonoid. So, the addition of ozone with alkene forms this, gives this intermediate ozonoid. Once we have this one, depends upon the reaction conditions. For example, if you use zinc in water, it can be converted into two molecule of formaldehyde. On the other hand, if you treat with oxidizing agent like such as hydrogen peroxide, it will be oxidized into formic acid. So, it depends upon, suppose if I take ethylene, I will get 2 molecules of formaldehyde. On the other hand, this is the mechanism of the ozonolysis. It undergoes 1,3 cycle addition, and once if you form this intermediate, it again undergoes a heterocycle addition reaction to give this carbonyl group and carbonyl oxide species, which undergoes further reaction to give this ozonoid. This ozonoid, when you treat with zinc water, is converted into the corresponding aldehyde. And instead of ethylene, if you take other alkenes, for example, unsymmetrical alkenes like propene, when you treat propene with ozone, and the presence of you will get this intermediate, addition of ozone with this propene can give this intermediate. When you treat this intermediate with the zinc, you will get acetaldehyde and formaldehyde. Similarly, when you react this substituted alkene, for example, this one, when you treat with ozone and followed by zinc, in this case you will get acetone and formaldehyde. It is a cleavage, oxidative cleavage reaction. You can selectively get the ketone and aldehyde. It depends upon the substrates, you will get the carbonyl compounds. The next example reaction is polymerization. So, all of us know, and so the polythene bags and plastic containers like quiz bottles, as well as TV and computer cabins, all are made up of polymers. One of the common polymers, for example, the polythene bags. You know that polythene is made from polyethylene polymer. And for example, when you have ethylene and using catalyst, high pressure and temperature, these three are very important. And this alkene, ethylene, can be converted into a bigger molecule. This one molecule is called monomer, and when you have they can react together and particular conditions, high temperature and pressure and catalyst, and give a bigger polymer. So, we write like this. So, this is called polymer. This is the material to make polythene bags and quiz bottles, so on. And if you look at the industries, and they produce about 80 million tons. tons of polyethylene per year we use, and of course, is not biodegradable polymer, but still we use, and yearly they produce about 80 million tons of polyethylene for various applications. And similarly, when you go for further propene also can be converted into polypropylene, and under high pressure, temperature, and catalyst. You can produce this polypropylene is produced about 50 million tons per year, and polypropylene, for example, bucket we use as a material, and these are widely used and for various applications, plastics. And if this is the highest polymer, and polyethylene based materials produced about 8 million tons per year, and this is the second largest polymer is produced about 50 million tons per year and used for various applications. And let us conclude today what we have seen: the chemical properties of alkenes. We have seen 8 type of reactions. First, what we have seen the addition of hydrogen, and that to alkenes that can lead to alkanes is a stereospecific specific reaction, syn addition reaction. Then we have seen addition of halogen. You can so iodine does not undergo addition with alkenes. However, chlorine and bromine can undergo addition with alkanes, and you get vicinal dihalo compounds. We also use this to check whether the compound has alkene or not. This, when the compound have double bond, they are called unsaturated compound. This one of the tests to check whether your compound is saturated alkane or unsaturated compound alkene. And what we do when we treat this compound with bromine. Bromine is a reddish orange liquid, and when you dissolve this compound in carbon tetrachloride, add bromine, if the color goes, we tell that the compound is unsaturated. This is one of the classical tests we use whether to check whether the compound is saturated, unsaturated by adding bromine. And what happens when you add bromine or chlorine and carbon tetrachloride, they can readily undergo addition reaction with alkene to give vicinal dihalides. It is an example for electrophilic addition reaction. Next, we have seen addition of hydrogen bromide to hydrogen iodide. Hydrogen chloride also can be added to alkene to give the secondary or more substituted alkyl halides. And this also an example for electrophilic addition reaction. By taking hydrogen bromide, we have seen, and you can form the more substituted bromo compound as a major product using electrophilic addition reaction. And this because of you generate a more stable carbocation as intermediate that undergoes a reaction with Br minus, you generate the alkyl halide. And so the reactivity of these halides, hydrogen iodide is more reactive comparing to a hydrogen bromide. Hydrogen bromide is more reactive comparing to hydrogen chloride. Then we have seen the peroxide effect in the hydrogen bromide addition reactions, and under this condition only hydrogen bromide undergoes addition with alkene to give primary alkyl bromide, and under this hydrogen chloride and as well as hydrogen iodide do not react with alkenes in the presence of peroxide, and in the case of hydrogen chloride it is very difficult to cleave the bond stronger than HBr bond. And in the case of hydrogen iodide, that iodine radical undergoes dimerization, can react with another iodine radical, you get the iodine. And however, hydrogen bromide can be added to alkene to give the primary alkyl bromide. In this case, what happens? You generate the radical intermediate. First, the bromide radical undergoes addition with your alkene, you generate the secondary radical that is more stable comparing to the primary radical. Therefore, that secondary radical undergoes reaction with even HBr to give the primary alkyl halide. This is called peroxide effect. This was discovered by Professor Harash and Mayo in 1933 in Chicago University, and this is called the peroxide effect. And basically, you get anti-Markovnikov product. In the case of electrophilic addition reaction, always you get the Markovnikov product. That more stable carbocation undergoes reaction with the negative part of this reagent. Then we have seen how you can convert alkene to alkyl sulfate. In this case, also the product is formed according to Markovnikov addition rule, because it is electrophilic addition reaction, you generate the carbocation that undergoes reaction, you give the alkyl sulfate, you get the secondary alkyl sulfate as a major product. Then we have seen addition of water to alkene, where you can make secondary alcohol. Under this condition, what you have to do, you have to treat with water in the presence of few drops of sulfuric acid. The reaction takes place quite nicely, you get the secondary alcohol. And then we have seen the oxidation using potassium permanganate depends upon the reaction conditions. You can selectively oxidize alkene to diol. Syn addition, basically both OH group comes the same side of the alkene, and whatever we have seen all are very simple substrates. When you take for example cyclohexene, then you can understand and you can get syn addition product, you get the diol the same side. If you use aqueous dilute cold KMnO4 at 0 degree, you get the diol product, 1 to diol product. And on the other hand, if you use slightly stronger reaction conditions like acidic potassium permanganate or dichromate, and then it can undergo further oxidation to give aldehyde. That aldehyde can be further oxidized to carboxylic acid. Basically, you get carboxylic acid the product. In this case, the potassium permanganate is reduced to manganese dioxide as a byproduct. Of course, the mechanism you will study in the higher class. And then we have seen ozonolysis. This is a very good experiment to cleave the carbon-carbon double bond to aldehydes or ketones, or then you can use when you the ozone undergoes addition with the alkene through 1,3 cycloaddition reaction to give the ozonoid intermediate. That ozonoid, when you do workup with the zinc or hydrogen sulfide, they undergoes cleavage to give the corresponding aldehyde or ketones. It depends upon the reaction conditions. If you use of course oxidizing agent like hydrogen peroxide, it also can be oxidized further into carboxylic acid. On the other hand, if you use reducing agents such as sodium borohydride, the aldehyde also can be reduced to alcohol. Depends upon the reaction conditions, and you can convert the alkene. You can cleave, then you can also further convert into alcohol or aldehyde, ketone or carboxylic acid. Depends upon the workup procedure. At the end, we have seen polymerization, how you can the alkenes can be converted into bigger molecule. This the ethylene can be coupled together, you make a bigger molecule, that is polymer we use as make very important commercial applications like plastic bags, containers, bottles, as well as computer and TV cabinets and so on. We use, and of course, we use for plastic purpose, and so mostly polyethylene is about just I mentioned about 80 million tons are produced annually in the world, and similarly polypropylene is the second largest polymer is produced, and that also we use for various applications. And similarly, other alkenes also are converted into polymers. They find wide applications. and these all polymers are made using different reaction conditions and higher temperature, pressure and catalyst. These are very important to get the polymer appropriate length and a particular stereochemistry also. The polyethylene is okay, but when you go for the other alkenes, the stereochemistry also very important. They can be controlled using appropriate reaction conditions. And with this I conclude today's lecture.